Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Zeta converter with improved voltage conversion gain Anson KAUG Student Electrical and Electronics Engineering Mar Athanasius College of Engineering Kerala, India Fidha Hashmi KPUG Student Electrical and Electronics Engineering Mar Athanasius College of Engineering Kerala, India Harikrishna UG Student Electrical and Electronics Engineering Mar Athanasius College of Engineering Kerala, India Jothis Jacob UG Student Electrical and Electronics Engineering Mar Athanasius College of Engineering Kerala, India Sera Mathew Assistant Professor Electrical and Electronics Engineering Mar Athanasius College of Engineering Kerala, India abstract demand for electricity is increasing day by day. However, due to the shortage of fossil fuels as well as their huge burden of environmental pollution, the proliferation of renewable energy systems is increasing. DC-DC converters are very popular and important because of the need for step-up of the low output voltage of most of these renewable energy systems. The traditional Zeta converter among other DC-DC converters has many benefits like low output voltage ripple and can be used to step up as well as step down the input voltage. It is difficult to apply the traditional Zeta converter in renewable energy systems as the voltage step-up capacity of the traditional converter is limited at high duty cycle due to the negative influence of parasitic parameters from the components. A single switch Zeta converter with improved voltage conversion ratio is used to address the issue. The converter not only achieves high voltage gain based on our requirement but also has considerably lower voltage stress across the switch. The voltage multiplier circuit is composed of passive components which ensures a continuous output current like the traditional Zeta converter. The drive and control circuits are simple and remain the same as the converter has only one active switch. The performance study is carried out with MATLAB/Simulink and simulation results are obtained. Keywords Zeta converter, switched capacitor, improved voltage conversion gain, DC-DC converter Introduction The use of electricity is increasing day by day with an ever-increasing population. This energy demand will be co-accelerated by the rapid industrial growth. This energy crisis, depletion of fossil fuels, an alarmingly rising level of environmental pollution and ever-increasing population are the primary reasons for stressing to switch over to renewable energy sources. 1. About 75% of the total CO2 emissions in the world is contributed by the power system's energy production sector. Thus, the UN is urging all nations to go green too. The non-conventional energy resources like photovoltaic, PV, modules, small wind turbines and fuel cells generate low DC voltage and need to be stepped up to the grid requirement voltage. A DC-DC converter is an electronic circuit that converts a source of DC from one voltage to another voltage. There are different types of traditional DC-DC converters like buck boost, COOC, SEPIC and Zeta converters. These are widely used for application in both industrial and commercial sectors. The increase in the use of renewable energy sources has increased the demand for high-gain DC-DC power converters that do not compromise efficiency. 3. Zeta converter is a fourth-order DC-DC converter that works as a buck-boost converter with a non-inverted output. It is also known as an inverting SEPIC converter, which is made up of 2 inductors and 2 capacitors capable of operating in either step-up or step-down mode. However, unlike the buck-boost converter, it does not give an inverted output and has the same polarity as the input. The benefits of the Zeta converter over the SEPIC converter includes low output voltage ripple as well as easier compensation. 3. In ideal conditions, by adjusting the duty cycle of the switch, any voltage conversion gain can be achieved. However, in actual working conditions, the boost capacity of these traditional converters is greatly limited by parasitic elements of the circuit and voltage drops across the switch and diodes. The conduction losses across the switch increase with higher duty. IJERT 10 is 060196 www.ijert.org 422. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Cycles. This makes the application of the converters difficult in situations where a large voltage conversion ratio is required, especially in renewable energy systems. To achieve a high voltage conversion ratio, a family of generalized passive voltage multiplier circuits termed code circuits are employed for. These circuits are termed code circuits for DC-DC converters because such circuits surround the DC-DC converters like a code. In addition to increasing voltage gain, these code circuits also reduce the voltage stress across the switch comparatively. A higher voltage gain can be achieved by employing a switched capacitor circuit in the traditional Zeta converter. This switched capacitor is formed by splitting the energy transfer capacitor in the traditional Zeta converter into two capacitors 5. The advantage of this topology is that there is only one active switch 6. The voltage boosting techniques presented in 6-7 either use transformers or coupled inductors which increase the losses in the converter. The proposed Zeta converter is shown in Figure 1. The converter consists of a single switch S1, 4 diodes DC, D1, D11, D12, 4 inductors L1, L2, L11, L21, 7 capacitors C1, CC, C11, C21, C2, C12 and output capacitor C22. Capacitors C1 and Fig 2. Equivalent circuit of converter in Mode 1 Fig 2. Theoretical waveforms Mode 2 is between the time interval, T1 to T2. The modes of operation are as follows: Mode 1, Fig 1. Proposed converter CC and diodes D1 and DC together constitute a switched capacitor combination. Capacitors C11 and C12, inductor L11 together with diode D11 constitute a single unit of the voltage multiplier circuit. To perform analysis of the converter, a converter with 2 units of the voltage multiplier circuit is considered. Some assumptions are considered during the analysis of the converter. They are as follows: 1. The capacitances of all capacitors are assumed to be large enough that the effects of voltage ripple across them are negligible. 2. All devices are assumed to be ideal, I.e., the influence of parasitic parameters is negligible. 3. Modes of operation. Since the proposed converter has only one active switch, there are only 2 operating modes in continuous conduction mode. These modes of operation are shown in Figure 2. Mode 1 is between the time interval, T0 to T1. Fig 3. Equivalent circuit of converter in Mode 1. In this mode, switch S1 is turned on and all diodes work in the off state. During this stage, the input voltage source charges the inductor L1. The capacitor C1 and CC discharge into the inductor L2 and the capacitor C2. The capacitor C11 and C1 discharge into the inductor L11 and the capacitor C12. Similarly, the capacitor C21, C11, and C1 discharge into the inductor L21 and the capacitor C22. Therefore, all inductor currents are found to increase linearly. In this interval, C2, C12 and C22 are charging while C1, CC, C11 and C21 are discharging. The equivalent circuit of Mode 1 is presented in Figure 3. The equations of Mode 1 are as follows: VL1 equals VN, VL2 equals VN plus VC1 plus VCC VC2, VL11 equals VN plus VC11 plus VCC VC12, VL21 equals VN plus VC21 plus VCC VC22. IJERT 10 is 060196 www.ijert.org 423. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 Mode 2, from Equation, 21, it is evident that the converter can be designed as per the voltage requirement. For design considerations, the input voltage is taken as 48V. The pulses are switched at a frequency of 100 kHz. The output power is taken to be 350W. Voltage conversion gain, M equals VO/Ven equals 4D/1D, where D is the duty ratio of the switch S1. D is taken to be 0.74. Fig. 4. Equivalent circuit of converter in mode 2. In this mode, switch S1 is turned off and all diodes work in the on state. During this stage, the inductor L1 discharges into capacitor C1 and Cc. The inductors L2 and L11 discharge into capacitors C11 and C21 through D11 and D21 respectively. The inductor L21 discharges through the output stage, C22/RL. In this interval, C1, Cc, C11 and C21 are charging while C2, C21, and C22 are discharging. The equivalent circuit of mode 2 is presented in figure 4. The equations of mode 2 are as follows: VL1 equals VC1 equals VCC, VL2 equals VC11 equals VC2, VCC, VL11 equals VC21 equals VC11, VC12 equals VC2 plus VCC, VC12, VL21 equals VC21, VC22 equals VC12 VC11, VC22, VL21 equals VC12 VC2 VCC, VC22, on applying the volt-second balance principle on the inductors L1, L2, L11, and L21 and considering the above analysis of the operation of the converter, we get the following equations. Ven D equals VC1, 1D, equals VCC, 1D, Ven VC2 plus VC1 plus VCC, D equals VC11, 1D, Ven VC2 plus VC1 plus VCC, D equals VC2 plus VCC, 1D, Ven plus VC11 plus VCC VC12, D equals VC21, 1D, Ven plus VC11 plus VCC VC12, D equals VC12, VC11, 1D, Ven plus VC11 plus VCC VC12, D equals VC12, VC2, VCC, 1D, Ven plus VC21 plus VCC VC22, D equals VC22, VC21, 1D, Ven plus VC21 plus VCC VC22, D equals VC22 plus VC11, VC12, 1D, 18, Ven plus VC21 plus VCC VC22, D equals VC22 plus VCC plus VC2, VC12, 1D, 19, the voltage conversion gain can be obtained from the above equations. It is shown in equation 20, M equals VO/Ven equals 4D/1D, 20, this converter can be generalized to contain n basic units of the voltage multiplier circuit. The generalized equation is as follows. M equals VO/Ven equals, n plus 2, D/1D, 21, A inductor design. The ripple current for the inductor L1, L1 204% of IO equals 1.35 A. Similarly, the ripple currents of the inductors L2, L11, L21 L2 equals L11 equals L21 52% of IO equals 0.35 A. L1 equals Ven dt L1 263.11 H, 22, L2, 11, 21 equals Ven dt L2, 11, 21 896.96 H, 23, to keep the ripple currents well within range. The value of the inductors is taken as L1 equals 300 H and L2, 11, 21 equals 950 HB. Capacitor design. The voltage ripple for the capacitors C1, Cc, C2, C11, C21 VC1 CC C2 C11 C21. 5% of VC1 CC C2 C11 C21 equals 6.83 V. The voltage ripple for the capacitor C12 VC12 5% of VC12 equals 20.49 V. The voltage ripple for the output capacitor C22 VC12 0.5% of VC12 equals 2.645 VC1 equals CC equals 3 IODT slash VC1 CC 2.157 F, 24. C11 equals 2 IODT slash VC11 1.483 F, 25, C2 equals C21 equals IODT slash VC2 C21 0.719 F, 26, C12 equals IODT slash VC12 0.283 F, 27, C12 equals IODT slash VC22 1.849 F, 28, considering the uniformity of devices and to keep the voltage ripples well within limits, the value of the capacitors C1 equals C2 equals CC equals C11 equals C12 equals C21 equals C22 equals 4 FV simulation results table I simulation parameters specification input voltage VEN 48V switching frequency FS 100 kHz output voltage VO 529V inductor L1 300H inductors L2, L11, L21 900 and 50H capacitors CC C1 C2 C11 C12 C21 C22 4F load resistance RL 800 IJERT 10 is 060196 www.ijert.org 424. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN 2278-0181 Volume 10 Issue 06, June 2021 Fig 5. Simulink model. The simulation parameters of the converter are shown in Table 1. A converter with two basic units of the voltage multiplier circuit is simulated. An input voltage VEN of 48V gives an output voltage VO of 529V for an output power PO of 350W. The pulses are switched at a frequency of 100 kHz. The duty ratio is taken as 0.74. The converter is simulated in MATLAB/Simulink by using the mentioned parameters. The Simulink model is shown in Figure 5. The simulation results of the converter are shown in the following figures. It can be seen from Figure 6. A and 6. B. That the input voltage VEN equals 48V and the output voltage is about 529V. The output voltage has a ripple of 0.017% which is very low and one of the characteristics of the Zeta converter. Fig 8. Inductor currents, A, IL1, B, IL2, C, IL11, D, IL21 Figures 7. A, and 7. B, represent the input and output current waveforms. The peak input current passing through the switch is equal to 12.67 A and the peak output current is equal to 0.661 A. Figures 8. A, 8. B, 8. C, and 8. D, are the inductor current waveforms. It can be observed that the current ripples are well within the designed limits. The voltage waveforms of the capacitors C2, C12, and C22 are shown in Figure 9. Fig 6. A. Input voltage VEN, B. Output voltage VO. Fig 7. A. Input current in, B. Output current IO. Fig 9. Capacitor voltages, A. VC2, B. VC12, C. VC22 IJERT 10 is 060196 www.ijert.org 425. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org International Journal of Engineering Research and Technology, IJERT, ISSN 2278-0181 Volume 10 Issue 06, June 2021 Fig 10. Capacitor voltages, A. VC1, B. VCC, C, VC11, D, VC21 Fig 12. Diode voltages, A, VD1, B, VDC, C, VD11, D, VD21. The voltages across capacitors C1, CC, C11 and C21 are -131.6 V, -131.6 V, -130.38 V, and -130.32 V respectively, and are shown in Figure 10. It can be observed that the voltage ripples of the capacitors are well within the designed limits. The voltage across the switch S1 is equal to 183.68 V and is shown in Figure 11. A. This voltage stress across the switch is low considering the large increase in output voltage. Figure 11, B, shows waveform of the switching pulses. Figure 12 shows the voltages across the diodes D1, DC, D11 and D21. They are 181.8 V, 181.8 V, 182.9 V, and 182.7 V respectively. 6. Analysis. The analysis of the proposed converter is performed by considering various parameters like efficiency, duty ratio, and output voltage ripple. From the plot of efficiency vs output power, the converter is found to have a maximum efficiency of 88.5% at a power of 864 W. Fig 11. A. Voltage across switch Vs1, B. Switching pulse VGS. Fig 13. Efficiency vs output power. On performing the analysis of voltage gain vs duty ratio, the plot in Figure 14 is obtained. The voltage gain is found to IJERT 10 is 060196 www.ijert.org 426. This work is licensed under a Creative Commons Attribution 4.0 International License. Published by http://www.ijert.org. Fig 14. Voltage gain vs duty ratio. International Journal of Engineering Research and Technology, IJERT, ISSN, 2278-0181 Volume 10 Issue 06, June 2021 7. Conclusion. The proposed converter offers improved voltage conversion gain and low output voltage ripple. This is achieved by the addition of a switched capacitor circuit as well as voltage multiplier circuits. On analysis and simulation, the proposed converter is found to have high voltage conversion gain. The number of basic cells of the voltage multiplier circuit can be adjusted based on different applications. Since the proposed converter has only a single active switch, the driver and control circuit are uncomplicated to design and cost-effective to implement. The converter helps avoid extreme duty cycles. These characteristics show that the converter is suitable for applications where a wide voltage conversion ratio is required. 8. References. Increase with increase in duty ratio. However, large duty ratios can result in larger conduction losses, thus reducing the efficiency of the converter. Therefore, large duty ratios are avoided. From Figure 15, it is observed that the output voltage ripple decreases with increase in the duty ratio. However, increasing the duty ratio to very high values is not practical as conduction losses increase. Fig 15. Voltage ripple vs duty ratio. Based on these and other parameters, the proposed converter is compared to the traditional Zeta converter as well as the Zeta converter with only voltage multiplier circuits. The comparison is given in Table 2. Parameters. Efficiency, output voltage ripple gain, input current, voltage stress of switch. Table 2. Comparison. Conventional code circuit 82.9%, 85.15%, 0.22, 0.165%, 0.1, 0.025%, 2.77, 11.604, a 184 V, 8.33, 11.825, a 184 V. Proposed 88.5%, 0.09, 0.017%. 11.02, 8.592, a 183 V1 RM. Ilavarison et.al., A Comprehensive Review on Renewable Energy Development, Challenges, and Policies of Leading Indian States with an International Perspective, in IEEE Access, Vol. 8, pages 744, 327, 4457, 2020, doi. 10.1109/access.2020.29888011. 2 W.G. Santika, T. Ermi, M. Anisuzaman, G. M. Shafiullah and P. A. Bari, Sustainable Energy for All, Impacts of Sustainable Development Goals Implementation on Household Sector Energy Demand in Indonesia, 2018 International Conference on Smart Green Technology in Electrical and Information Systems, ICTIS, 2018, pages 13 to 18, doi. 10.1109/xtis.2018.87091108. 3 P. R. Babu, S. R. Prasath and R. Kairuthika, Simulation and Performance Analysis of CCM Zeta Converter with PID Controller, 2015 International Conference on Circuits, Power and Computing Technologies 2015, 2015, pages 1 to 7, doi. 10.1109/2015.7159506. 4 Biju, F. Ding and D. M. Vilath Gamuwa, Code Circuits for DC-DC Converters to Improve Voltage Conversion Ratio, in IEEE Transactions on Power Electronics, Vol. 35, Number 4, pages 3679 to 3687, April 2020, doi. 10.1109/TPEL.2019.29347226. 5 B. Axelrod, Y. Berkovich and A. Ioinavisai, Hybrid Switched Capacitor Cuck/Zeta/Sepic Converters in Step-Up Mode, 2005 IEEE International Symposium on Circuits and Systems, 2005, pages 1310 to 1313 Volume 2, doi. 10.1109/ISKIS.2005.1464836. 6 S. Arfin, A. Al-Mamun, T. Chowdhury and G. Sarawar, Zeta-based hybrid DC-DC converter using switched inductor and switched capacitor combined structure for high-gain applications, 2019 IEEE International Conference on Power, Electrical, and Electronics and Industrial Applications, PIACON, 2019, pages 1 to 4, doi. 10.1109/PIACON488440.2019.907190. 7 M. Forozaj, Y. P. Sawakati, S. A. Gorgi, F. Blobjig and B. Lehman, Step Up DC-DC Converters, A Comprehensive Review of Voltage Boosting Techniques, Topologies, and Applications, in IEEE Transactions on Power Electronics, Vol. 32, Number 12, pages 9143 to 9178, December 2017, doi. 10.1109/TPEL.2017.2652318. 8 Biju, S. Hu, G. Lu, Y. Huang and X. Shi, Low Voltage Stress Buck Boost Converter with a High Voltage Conversion Gain, in IEEE Access, Vol. 8, pages 95188 to 95196, 2020, doi. 10.1109/access.2020.29958889. 9 W. Lee and X. He, Review of Non-Isolated High Step-Up DC/DC Converters in Photovoltaic Grid-Connected Applications, in IEEE Transactions on Industrial Electronics, Vol. 58, Number 4, pages 1239 to 1250, April 2011, doi. 10.1109/Ty.2010.2049715. Tenju, Binkson, Wang, Han, and Vilath Gamuwa, Don Mahinda, 2019, Single Switch High Step-Up Boost Converter based on a novel voltage multiplier. IET Power Electronics, 12, 14, pages 3732 to 3738. 11 J. Reginaldo de Brito, A. Elias Demian Jr., L. C. de Freitas, V. J. Farias, E. A. A. Coelho and J. Batista Vieira, Zeta DC/DC Converter used as LED lamp drive, 2007 European Conference on Power Electronics and Applications, 2007, pages 1-7, doi, 10.1109/EPE.2007.44174112. IJERT 10 is 060196 www.ijert.org 427. This work is licensed under a Creative Commons Attribution 4.0 International License.